Alright, so today we will continue the lecture on proof by induction. And since it's been some time, so let me remind you what we are at. So we want to prove some property that depends on some parameter n. So when I say 1 plus 2 plus up to n, the sum of first n natural numbers is actually equal to n times n plus 1 over 2. This sentence is a single line, but it actually encodes multiple facts. So it could be when n equals 1, n equals 2, n equals 3, and so on. So one naive idea is can we enumerate these all cases, and that means you can check one by one. Okay? So for your peace of mind, you can take n equals 1. That means in the left hand you have only one term to add. Okay, and check with the right hand side. Okay, this is true. When n equals 2, you check it and it feels right. N equals 3. Okay, you get it done. The fact is you cannot go on forever. Okay, but you may say why is not enough, because I checked most of the cases, or maybe cases it seems to be it's a law. It cannot be violated. And we talk about this fact that this 2 to the power of 2 to the power of n plus 1 is a prime number. So actually first 4 cases were true, but suddenly when n equals 5, this is no longer a prime number. Okay? And this is something that we also taught in the beginning of the semester. This is Wolbach's conjecture. Every even integer greater than 2 is the sum of 2 prime numbers. So you can play with it. 4 is equal to 2 plus 2, 6 is equal to 3 plus 3, 8 equals 3 plus 5, and so on and so forth. You can actually go maybe many digits, and people already have tried, and they couldn't find a counterexample to that claim yet. But does it mean that this is actually true? Nobody knows, right? Who knows? Maybe very big numbers may not be represented by some of 2 prime numbers. Okay? So enumerating the cases gives you some idea that it might work. Okay? But it doesn't prove that this is true. Okay? So nobody was able to find a counterexample. Doesn't mean that there is no counterexample. Okay? Even with the computer, okay, you can write a for loop, you can generate everything, and you can try to find 2 prime numbers that can add up to these even numbers. You may want to do that, but maybe for your lifetime, if you succeed, then you can publish a paper. If not, then it's a waste of time. Okay? So what people found out was there was actually a better way to prove these kind of claims that depends on n, where n ranges over infinite possibilities. Okay? So to prove such a claim, what people found out is let's try to prove in a different way. Okay? So try to prove P1. The same as before, but when you try to prove P2, let's try to prove this claim. P1 implies P2. If P1 is true, then P2 is true. Okay? And also going repeatedly doing that. So if P2 is true, then P3 is true. If P3 is true, then P4 is true, and so on and so forth. Wait, what is going on? Why are we making the problem harder? Does it actually help anything? Well, we just talked about enumerating the cases does not help us, right? So P1, check. P2, check. P3, check. P4, check. It doesn't help us. Same way, if I prove this P1, and then P1 implies P2, P2 implies P3, P3 implies P4, P4 implies P5, doesn't help us anything, right? But before we do that, let's first understand whether they are actually getting the same conclusion. So why do they derive the same conclusion? Okay. So suppose for the time being, you can do infinitely many computations. Okay, P1, P2, P3. Or you can do P1, and P1 implies P2, P2 implies P3, P3 implies P4. Suppose you can do that infinitely many times. Suppose. Okay? Do they actually do the same thing? It doesn't seem so, but let's try to apply the natural deduction. So we know P1 is true. Okay, that's good. That's actually same as P1, right? What about these two things? If you see these two formulas, what can you conclude? So what can you conclude there? I'm just curious what you're next up to. So if you can show on the left, right? So P1, so let's first look at the first two lines. P1 and P1 implies P2. What can you derive? Huh? P1? P2, yes. P2 can be derived from using which rule? Implication elimination rule tells us that we can derive, actually let me just write P2, okay, by implication elimination rule. So let me actually write down this again. So from these two, we can derive P2. And using the implication elimination rule. Okay, so we know now P2 is true, given the first two lines, right? Now suppose we can also prove, actually let's assume that we know that all these are provable. We already proved this. Now with the first two we can also derive that P2 is true. Now what about P2 and this one? Suppose now P2 is derived using implication elimination rule. But we also know that P2 implies P3 is another formula that we know for to be true, right? So what can we derive now? P3. Okay. So given this, we can derive also P3. But knowing now P3 is derivable, and also we know that P3 implies P4 is true, what can you derive? P4. And basically, if you follow this way, P1, P2, P3, P4. P1, P2, P3, P4. We're actually proving this for all cases, right? The only problem is, like the previous one that we did, how can we show these infinitely many formulas? Pn implies Pn plus 1. Okay? Now, surprisingly, this is the right-hand side here. This is actually hard to apply this induction idea. But suddenly, if you write this fact in a slightly more complicated way, while you can derive the same conclusion, you can actually make this thing to be shrinking in one step, which is called inductive step. The magic here is when you prove this fact, P1 implies P2, P2 implies P3, P3 implies P4, P4 implies P5, P5 implies P6, P6 implies P7, all the way down here. We're actually using exactly the same kind of reasoning. So you can abstract this away, but you can write this step as one step instead of many, many, many steps. Okay? So, here is the induction principle that you saw before. So first, we need to identify what is the sentence that we want to prove. And the first thing that I ask you to do for all the homework and all the quiz, all the tests, all the exams, is identify what is P of n that you want to prove. Many of the times you actually forget about it and the proof is not readable at all. Okay? So what is P of n that you want to prove? First, P of n must be a declarative sentence, meaning that it's either true or false. It can be evaluated to be true or false. Okay? Another thing is n is a parameter. Okay? N can range over all natural numbers, but sometimes it can be starting from different from 1, but anyway, this n ranges over some integers. Okay? So you have to identify what is P of n. And what you are doing is these two steps. So first, base case is the same as what I said, so prove that P1 is true. Okay? So the claim calls for when n equals 1. The second one is inductive step. Okay? So for the inductive step, you are proving this fact, P of n implies P of n plus 1. What does that mean? So first, what is this sentence, P of n implies P of n where m here is a parameter, okay, for induction. So I wrote this as a one line, but you will notice that this is basically the same as what I wrote in previous slide as a multiple lines. I wrote as just one line, but this line expands into multiple lines here. Do you get this? Okay? This line that you saw is just shorthand for multiple lines. Okay? Now one big idea here is all these steps repeat the same reasoning. So we are going to abstract away the reasoning so that we can just write one case, which is called inductive step. Okay, so we are going to prove this claim. If P of m holds, then P of m plus 1 holds. Now one thing to be careful, I told you multiple times by now, when you see this line, if P of m holds, then P of m plus 1 holds, your job is not to prove P of m. P of m is an assumption that is given to you. Okay? So in the natural deduction, this kind of sentence was like this. Okay? P of m is an assumption. You don't argue about the assumption. Given the assumption, your job is to go into P of m plus 1. You have to fill the box. That's your main goal for the inductive step. Okay? So in terms of natural deduction, the inductive step is saying that you have to fill this box. Starting from P of m, try to prove P of m plus 1. Okay? Now there is actually quite an interesting thing here. What you try to prove is P of m plus 1. What you know for true, what you know as a truth in the assumption is P of m. And these two sentences have very similar form, except the parameter is different. Okay, m versus m plus 1. So basically the sentence has exactly the same structure except for this parameter. Okay? So P of m is called induction hypothesis. This is probably the final time that I will say, don't argue about induction hypothesis. You have no right to do that. Okay? All right, so now what induction principle tells us is if you prove this base case and inductive step, then the conclusion follows. The conclusion is P of n is true for all possible n. And we saw in the previous slide why this is the case, right? If we know that P of 1 is true, but in the base case, we assume we prove that P of 1 is true. Okay? And in the inductive step, we are basically proving all these things. And now using this cascaded reasoning, okay, from these two formulas, you can prove P of 2 is true. Once P of 2 is true, then using this one together, you can derive P of 3. And then P of 3 together with P of 3 implies P of 4, you prove P of 4, and so on and so forth. Okay? Are we together? Okay. So you didn't prove the induction assumption to be true, but the fact that this is true is established from the previous case. You didn't prove, when you're using this induction hypothesis, you didn't prove P of 2 is true. But the fact that P of 2 is true is coming from the previous two steps. Same way all the down. So again, I emphasize, or maybe I contradicted myself, when you prove each of these claim, or this box, don't worry about P of m. Okay, so this was the example that you saw before. Okay, the first step is to define P of n. So what is P of n for this example? P of n means that 1 plus 2 plus up to n equals n times n plus 1 over 2. This equality is true. Okay, so base case, okay, this is easy to do. Inductive step. The first line that you have to write, okay, is assume that P of n is true. It's like a natural deduction style of proof that I show you what is the template of the proof, right? Same as here, induction also has a template, okay? So far, I don't expect any guess here. You have to just write these things. If I don't see these lines, you'll get 0 for the solution because this is very basic thing, okay? Alright, so actually I have typo. I should actually write this is m plus 1 over 2. Sorry about that. So assume P of m is true. So 1 plus 2 plus up to m equals m times m plus 1 over 2. Okay, I think I should change all n to m. Okay, so we assume that P of n is true. Okay, and then we are trying to prove P of m plus 1. Okay, now these two sentences have the similar form, but we know that this is true. We don't know that this is true. It's our goal to prove this line is true. And how do we do that? Well, let me write m here. So let's say 1 plus 2 plus up to m plus now m plus 1. This is the left hand side, right? And our goal is to prove that this whole thing is same as on right hand side. Okay? It's tedious to write this. So as you see, the first sum of m numbers is same as m times m plus 1 over 2. Why? Because induction hypothesis. And then you can copy m plus 1 and m plus 1 here. Okay? So the first step is using the induction hypothesis. We write that. The next one, okay. Let me write. So next one is just a pure algebra, okay? Because we have to add up these two, but the denominator are different. So let's just multiply 2 to each numerator and denominator for the second term. So then you can add these things, okay? So m. Now once you do that, m plus 1, so 2 is a common denominator and m plus 1 is a common factor, right? So you can factor out m plus 1 over 2. And then remaining is m plus 2 here. So you just factor out the common factor. And this is again an algebra. Okay, so you get it. Now once you do that, you realize that this one is exactly the goal that we wanted to prove, the right hand side. Okay. So in these steps, we use induction hypothesis, and after that we use algebra property and found this. Okay. Any question about this proof? Okay, if not. So we are going to exercise a few more things. But we actually look at this one too. So any set of n horses have the same color. Okay? So P of n here means that any set containing n horses have the same color. And base case is very clear because if there is only one horse, then only one color there. Now assume that the induction hypothesis is true. That means if you pick any set of m horses, they have the same color. So since we know that is true, consider any set that containing n plus 1 horses. And this, we can actually extract two sets of horses from this m plus 1 horses. The first set is taking the first m horses, so that is h1 through hm. Okay? And since this set contains only m horses, induction hypothesis apply. Don't argue about induction hypothesis, right? Because that's given to you. Okay, somebody was arguing about it last time, but I keep saying that don't argue about it. Okay? Because we just proved that that's not the point. Now consider the second m plus 1 horses. So h2 to hm plus 1. Skipping the first horse, but all the remaining horses, there will be still m horses. And they all have the same color. So what happens here is, if we do, so we consider this h1, h2, hm plus 1 horses. So total, there are m plus 1 horses. But we are dividing into two groups. The first m horses, this is the first set, and the second set is, starting from h2, that's another set of horses. And each set should contain only one color. Okay? So the first set has color 1, second set has color 2, but then these two sets have the common horses, h2 to hm. So that means these two colors in each step are actually the same color. Okay? So that means all those forces from H1 through Hn plus 1 should be equal. Okay, and that proves the induction step. Okay, so what's the wrong sentence here? What is the wrong sentence? The answer is D. Why?
Because from H2 to Hn, only one horse can only have one color, right? It can have
Right.
each set has different colors.
Mm-hmm. Yes.
And
And what's wrong is that?
what's common between those two sets of the same horses, right?
Mm-hmm.
They can have two colors. It's only one color. However, there's two different colors in those that separates those two sets. Right?
So yeah, so which sentence are you saying is wrong?
It's so we wait, the first one.
The first one.
H2, Hn are common.
Why they are not common? Why? Why this is false? So if you have H1, H2, H3 versus H2, H3, H4, then H2 and H3 are common. So that seems to be fine. Right? Isn't it? So let's say, sorry for making a horse, but horse 1, 2, 3, no, horse 2, 3, 4. And these two guys are common, right? They cannot have two different colors. So all these four people have the same colors. All these four horses have the same color. Okay? So what's wrong with this idea? Yeah? Yes.
Well, it is true that horse 2 is horse 2. That doesn't account for horses plus 1.
Horse
Plus 1.
and
Is that just going through?
n equals 1? Is that what you're saying?
First and last element, like
Yeah.
different colors, right?
Yeah. So I think he has the right point there. So this one is not true for all m. When m equals 1, let's see what happens. When m equals 1, that means we have two horses, H1 and H2, when m equals 1, right? Because here we are considering m plus 1 horses, right? Right? So let's take the first m horses, where first one horses, that's H1. So this is actually, let me write here, this is the first step. So I'm actually instantiating this, this one when m equals 1, and let's see what happens. When m equals 1, okay, there are only two horses, H1 to Hm plus 1, m equals 1, so m plus 1 is 2. The first set contains m horses, or one horse, so that's the first set, and the second set is this. And now, 1 and 2, those two sets have no common horses. If m is at least 2, there will be common horses. But when m equals 1, this does not work. Okay, in the homework, I will give you some tricky questions like this, and you have to find out what is wrong with this inductive proof. Let's actually zoom out. What is wrong with this argument? Where the induction actually is wrong. One advice that I can give you to you when you try to identify the mistakes in the induction, try to instantiate this argument. Okay? Don't just believe m is anything that I can write like this. Try to write one by one. Okay? So as I told you before, induction step is basically proving these set of implications, right? So this is the base case and this is inductive steps, right? Now if you have turn this into this way, you can easily find out what is wrong here. So P of 1, is it true? That is true. If you have one horse, then it's true. So this part is okay. Now what about P of 1 implies P of 2? P of 1 means if you take only one horse, okay, and that horse has only one color, right? Then if you take two horses, then they have the same color. Is it true? You can easily find a counterexample, okay? Two horses, red and blue. That doesn't seem to be like a real horse colors, but let's say red and blue, okay? So each of the horse has one color, but if you mix them up, this is still two colors, it's not one color. So the induction step actually fails here because there is no common horse between the two sets. Okay? What you will see is actually these steps are fine. This is actually true. This is actually true. If you have two horses, if you have a set of any two horses that have only one color, then you can prove that any set that contains three horses also have the same color. You can prove it because in that case you have, so in that case you have H, let me say, you can, so this case you can say, suppose you have these two horses, they have the same color. And H2 and H3 also have the same color. Then these three horses have the same color. You can prove it. Because once m equals 2, these two sets can have common horses. The only case that this induction fails is P of 1 implies P of 2 is not true. Because in that case, there is no common horses between the two sets. So the counterexample that I just described is this one. You have two horses, okay? And each set containing one horses. Now, these two sets, H1, singleton set H1, singleton set H2, do not have common element. So you cannot argue like this. All right, that's good. So here's some variations of mathematical induction. This is just good to know when you see some variant problem. It's not really difficult to understand, but because of the indexing, some people may find it difficult. Sometimes induction doesn't necessarily start from 1. It may start with some number 4, or number 5, or number 100. Okay? So let's pick any n0. Okay? So what you do is you try to prove this case for P of n0. Okay, n0, let's say n0 is 4. Then the base case is now P of 4. Okay? So base case can be P of 4. And then what you prove is P of m implies P of m plus 1. But this time, m starts from 4. Okay, so that is what this is saying. So the base step is you prove for the given first number, which is P of n0. Inductive step is you're proving the same claim. If P of m is true, then P of m plus 1 is true. But now this m starts from this n0. That's the only difference. Okay? But as you can argue, this thing is same as P of 4. And then this thing expands into P of 4 implies P of 5. P of 5 implies P of 6. P of 6 implies P of 7, and so on and so forth, right? And using the same reasoning that you did before, with these things proven, you prove P of 4, P of 5, P of 6, P of 7, and so on and so forth. However, this one doesn't tell you anything about P of 1, P of 2, P of 3. This proof does not establish those things. Okay? Any question? There's a difference in the indexing, which is actually a minor thing here. So here the base case is, let's say, same as P of n0. Now some books have induction stating this way. So if P of m minus 1 is true, then P of m holds. But here m is greater than n0. And again, if you instantiate this, so let's say n0 equals 4. Okay, so the base step is to prove P of 4. And inductive step is proving this when m is greater than n0. So m starts with 5, but if P of m minus 1, then this is m minus 1 is 4. So you get this one. Okay, when m equals 5, m equals 6, then you get this one, and so on and so forth. And as you see, this thing is same as this thing. Okay, it's just a different indexing that some books to use. Okay, if you are confused about what indexing, my advice to you is again instantiate this and check whether you are not missing anything. Sometimes I see the proof from the students that the indexing was messed up, so somehow it skips one of these cases, and of course that's wrong. All right, good. Now, the second topic is course of values induction, which is known as strong induction. Sometimes people say the mathematical induction is a weak induction, but our textbook says that course of values induction versus the mathematical induction. Can you? All right. So in course of values induction, what we are showing is actually this one. Okay. So P of 1, and then P of 1 implies P of 2. P of 1 and P of 2 implies P of 3, and so on and so forth. So what is this thing? First, what is the difference between this one and the mathematical induction? What is the difference? So, showing these series of formulas, okay, that's the course of values induction. And what was mathematical induction? There's a few slides before. Okay, so let's look at this picture. So here we use P of 1, and then P of 1 implies P of 2, P of 2 implies P of 3. Okay? How many formulas do you see on the left-hand side of the implication? 1. Okay. So the next, we see this. So this time we see more formulas on the left-hand side, right? So now let's see what is going on. Are we proving the same thing? So suppose we know that these two formulas are true. What do we derive? The same as before. There's nothing new here yet. P of 2. Now, we know P of 1 is true. Also P of 2 is true. Then their conjunction is also true by conjunction introduction, right? So we know that at this point P of 1 and P of 2 is true. Now with this one and this one, what can we conclude? P of 3, of course. Now we know that P of 3 is true and this is true. Then we can derive P of 1 and P of 2 and P of 3, right? And with this one and this one, what do we derive? P of 4. As you can see, we are still doing the same thing. P of 1, P of 2, P of 3, P of 4, and so on and so forth. Again, you are making the formulas more complicated than before. Okay, I will tell you why we want to do this. The thing to notice here is we are going to show only one step for the proof, which is this one. The whole sequence of this, including even the base case, can be summarized by only one line. Okay? So we are assuming that this property holds for all the values preceding n. So from 1, 2, up to n minus 1. We assume that this property holds for all such preceding numbers. From these assumptions, we can derive P of n, and we are done. Okay? So, when you prove this claim, how many induction hypotheses do we have? How many induction hypotheses do we have? N minus 1. We know that P holds for 1, P holds for 2, P holds for n minus 1. So we have n minus 1 induction hypothesis at hand. How about mathematical induction? How many induction hypotheses did we have?
One.
Only one. So which is better? When you prove in natural deduction, what was easier? When you have more formulas at hand or less formulas at hand? More formulas. Because you have more rules to apply, you have a better chance to prove. So this is the beauty of strong induction. While it shows the same conclusion as mathematical induction, the benefit is you have more assumptions to use. So the proof sometimes become easier. Okay? So I will show you some examples, but before we do that, I just want to emphasize. Here, the base case is also covered by the one line. Okay? So what happens? When m equals 1, this sentence, this is a bit tricky, so you don't, let's say this way. So I'm going to tell you in two ways. One is, there's actually no base case needed for this kind of proof, because when m equals 1, this is empty. Okay? So you have empty conjunction, which is same as top or true. So that goes back to this one. So when this is empty, when m equals 1, this is still same as P of 1. Okay? So this case, the inductive step, actually covers the base case too. That's where strong induction is a bit different from mathematical induction. In mathematical induction, base case cannot be covered by inductive step. That's a somewhat technical question. Some people say this in two steps. I think our textbook also follows that tradition because of pedagogic reason. Sometimes people call it still this is a base case, and this case as inductive step. Okay, so there's some slight confusion among different textbooks. Okay. Personally, I think this is much better because base case is still part of the inductive step. It covers naturally. Okay. All right. So there's something about base case. Now let's talk about why this kind of strong induction is needed. So there's something called Fibonacci number. Have you seen the Fibonacci number before? Yes. Okay, good. So long time ago, somebody in Italy was trying to count rabbit, and the rabbit grows rapidly. So in 1 month, it can produce a baby rabbit. Okay. So what he observed was there was no rabbit in the beginning. But let's say In the first month, there is a baby rabbit. Okay? And it takes 1 month for the baby rabbit to be a mom rabbit. Okay? Once the mom rabbit is an adult rabbit or mom rabbit, it can produce 1 baby. Okay? So then, in the 3rd month, how many rabbits are there? How many rabbits are there? 2. Why? Because the mom is still there, and this mom gives birth to a baby rabbit. Okay? In the 4th month, how many rabbits will be there? Hmm? 3. Because this mom is still there, but it also produces a baby, while this baby rabbit takes 1 month to grow. So there are 3 rabbits. Okay? In the next month, how many rabbits will be there? 5. Because this rabbit produces still constantly giving a birth, while this one takes 1 month to grow, and this rabbit can give a birth. Okay. So when you see this sequence, it turns out that when you count, say, month 5th is a 5, but 5 is equal to 2 plus 3. And month 4, the number 3 is equal to 2 plus 1. In month 3, this 2 is equal to 1 plus 1. In month 2, this is equal to 1 plus 0. So if you add the 2 previous months' rabbit number, then you can find out the number of rabbit and in n months. So here is the series defined recursively. So Fibonacci number 0 equals 0, fib of 1 equals 1, fib of n, where n now starts from 2, is equal to f of n minus 1 plus f of n minus 2. Now note here carefully, I see a lot of mistakes, the same mistake despite how many times that I say in the class. Sometimes you forget that n in the last equation starts from 2. Okay? So this is a recursive definition, meaning that f of 2 is defined as f of 0 plus f of 1. F of 3 is equal to f of 1 plus f of f of 2 plus f. Let's just write in the order. Okay? So f of 1 plus f of 2 and so on and so forth. Okay, so this is a Fibonacci number. Okay? Now, okay, let me. So this is the claim that we want to prove. Now show that every Fibonacci number of n is less than 7 over 4 to the power n for any n that is greater than or equal to 0. So how do we prove this fact? So we'll show this one. Okay. So according to the induction principle, okay, let me actually show you what we have to do. Okay. So we need to show this fact. Okay. So here n0, the starting point is not 1 because Fibonacci number starts from 0. Okay. But anyway. Here, there's a still typo here. Okay, so this should be n0. Okay, so here we are assuming the induction step. Okay, so what we want to prove is P of m is true, and for that we can assume all the preceding cases the property holds. So P of n0, P of n0 plus 1, P of n0 plus 2, up to P of n minus 1. In, the property holds. From this, we want to prove that P of m is true. Okay? So having done that, let's try to prove this claim together. Okay? We can try to prove this by, I don't know, enumerating. So you can do f of 0, f of 1, f of 2, f of 3, and so on and so forth. Okay? Or we can use strong induction, because we are so busy we don't have time to go through infinitely many cases. So first, very first step of any induction. What is the very first step?
Base case.
No, even before that. You have to identify what is the statement that you want to prove. Let's write that statement as P of n. What is a P of n in this problem? Shown there. P of n means f of n is less than 7 over 4 to the power n. So how do you prove this?
For 0 and 1, we have to kind of manually do that formula.
So we have to prove this for all values of n. Now the Fibonacci number is defined as separately in the base steps, okay, base cases and inductive recursive cases. So let's first prove P of 0. P of 0, what is P of 0 meaning? Means is f of 0 is less than 7 over 4 to the power of 0. Is it true or false? Why? What is f of 0?
0.
And what is 7 over 4 to the power of 0? So 0 is less than 1, so this is true. What about P of 1? P of 1 means f of 1 is less than 7 over 4 to the power of 1, right? Is it true? Yes, because f of 1 is 1. 1 is less than 7 over 4. Now, we want to now do the inductive step, okay? So let's assume, so we want to prove, so our goal is to prove P of m, but what can we assume for induction hypothesis? According to the strong induction, you can use any preceding numbers. Okay? We can assume P of 0 is true, P of 1 is true, P of 2 is true, up to P of m minus 1 is true. Are we together? Okay. So now let's talk about P of m. So we assume that these preceding cases are true. Now we want to prove P of m. P of m means f of m is less than 7 over 4 to the power of m, right? But before we show that, so I don't know how many space that we need. The goal here is to show that f of m is less than 7 over 4 to the power of m, right? And this is the whole box that we want to show now. Okay? So first, let's apply the definition. F of m is equal to right? Why this is true? That's the definition of Fibonacci number. Yes, that was given. Okay? Now, I'm going to use induction hypothesis for Pm minus 1 and actually Fm minus 1 and f of m minus 2.
They said they would send.
Okay, thank you. So for f of n minus 1, what does the induction hypothesis tell us? Yes, this one, right? Fibonacci number f minus 1 is less than 7 over 4 to the power of n minus 1. n minus 2 is this. So this is induction hypothesis, right? Are we together? We are proving the similar statement as in the induction hypothesis. We are proving f of m is less than 7 over 4 to the power of m. Now what we have at hand among the many induction hypotheses, these two, so this is f hypothesis will be useful. Fibonacci number m minus 1 is less than 7 over 4 to the power of m minus 1. And similarly for m minus 2, Fibonacci m minus 2 is less than 7 over 4 to the power of m minus 2. Okay, using the induction hypothesis, we know that this is smaller than this, know that this is smaller than this. So sum of these two Fibonacci number is less than the sum of these two numbers. Are we together? Okay. This is a step that I use induction hypothesis. And then what I do, I use only algebra. So this number has common factors, which is 7 over 4 to the power of n minus 2. Then what are the remaining factors? So these two have common factors 7 over 4 to the power of n minus 2. So if I factor out 7 over 4 to the power of n minus 2, what should I write here? So 7 over 4 to the power of m minus 1 is equal to 7 over 4 to the power of m minus 2 times 7 over 4. Do you know this fact? Okay. Knowing this fact, if you factor out 7 over 4 to the power of m minus 2 from the first term, what remains? 7 over 4. Now what remains from the second one? 1. So you get this one. Okay, if you don't know about these rules, then you have to review the high school algebra. Okay, if you don't know, come to our office hours if you don't want to get penalized for these things. Okay, it will happen in your test. Okay? All right, so this is 7 over 4 to the power of m minus 2. And this is 7 over 4 plus 4 over 4, right? So that means this is 7 over 4, m minus 2, and this is 11 over 4. Right? Are we together? And this one is less than 7 over 4 to the power of m minus 2 times 49 over 16. Maybe let me write more steps here. So 11 over 4 is less than 49 over 16 because this is same as 44 over 16. 44 is less than 49. Okay? And what is this number? 7 over 4 to the power of m. Okay? So what I show is from the beginning, f of m and series of the algebraic manipulation show that the number f of m is less than 7 over 4 to the power of m. Okay? So that's the inductive step. Any question about this proof? So you can do that if I give you a quiz, right? Okay. Now, why this proof is course of values induction rather than mathematical induction? So I used induction, right? So why is it called course of values induction rather than mathematical induction? Yes.
It's gonna do like with the mathematical induction, it's about finding like a general rule. Well, this is about like the sequence of numbers.
Not necessarily. They actually can be used for the same kind of proof. But this particular proof is not in mathematical induction. The form is very, very different. So in mathematical induction, how many induction hypotheses can you use? One. Here, how many did I use? How many? Two. I use induction hypothesis for f of m minus 1 and f of m minus 2. I actually can use more than that, but I don't need. Okay? So I can use only the first two preceding numbers, f of m minus 1 case, f of m minus 2 case. I use two induction hypotheses. In mathematical induction, you can never use more than one induction hypothesis. There's only one induction hypothesis can you use. And that's only the one that just precedes the current number. If you're going to prove the case for m plus 1, you can only use the induction hypothesis for m. Okay? But here, to prove the case for P of m using the strong induction, I can use all these n minus, actually n, P of 0 to m minus 1 is there m induction hypothesis I can use. I don't have to use all of them. I can choose whatever that I like to do. And for the Fibonacci number, these two cases, m minus 1 and m minus 2 are handy. Okay? All right. So now let's use this induction hypothesis, induction method for proving that all Fibonacci numbers are even. Okay? So assume that all f of 0 to f of n minus 1 up to f of n minus 1 are even. This is induction hypothesis. Okay? By definition, f of n equals to f of n minus 1 plus f of n minus 2. The Fibonacci number, right? So we know by induction hypothesis, this is even, this is even. When you add even and even number, what is the result? Is it odd? No. When you add two even numbers, the result is always even. So, what did we just prove? F of n is equal to f of n minus 1 plus f of n minus 2. By induction hypothesis, f of n minus 1 is even, f of n minus 2 is even. When I add up, f of n is also even. So I prove that all Fibonacci numbers are even. True or false? It's false. But the question is, which part is wrong in the proof? And we are going to open this operative. Okay, let me just this. Okay, so let's see how we do. The question is, there are three sentences. Which sentence is wrong? Okay. So the question, or the proof goes like this. We're using the photo values induction. When you want to prove the property for some number m, or n in this case, okay? So we want to prove f of n is even. By photo values induction, we can use the induction hypothesis for all the numbers preceding n. That means f of n minus 1 is even, f of n minus 2 is even, up to f of 0 is even, right? All the preceding Fibonacci numbers are even. That's by induction hypothesis. And since Fibonacci number is the addition of two preceding numbers, and all the two preceding numbers are even, right? So even plus even must be even. So f of n is even. So we proved this by induction hypothesis, and by causal values induction, then all Fibonacci numbers must be even. Okay? It's very surprising result here. Okay? So let me show you how your peers did. So there's no D as a choice. Okay? So that's surprising. And despite the warning that I gave you multiple times throughout the lecture today, about 49% here didn't pay attention to what I said. Okay? I said multiple times today, don't argue with assumption inductive hypothesis. Don't argue with them. A is not the answer. Okay, so who chose B? B is the right answer. What's wrong with B? What's wrong with B? I told you again a few times that this equation starts from when n equals 2. Okay, so that's what we want. Okay, now let's think about what is actually going on in this proof. So let's try to show this by instantiation. That is the technique that I told you to try. If we are going to do this by strong induction, what you are showing is basically this one. So this is what induction. Okay, what is going on? Hey, let me just write. It's not my intention to change the color, so you can ignore the color change. So what strong induction is showing is these series of sequences, right? So P of 0 is true. If P of 0 is true, then P of 1 is true. If P of 0 and P of 1 is true, then P of 2 is true, and so on and so forth. Okay? So what is wrong here? P of 0. These two cases are not covered by the definition, because Fibonacci number of 0 and Fibonacci number of 1 is not defined by that equation in second line. So you cannot say that. And actually, let's see what is going on. P of 0 means Fibonacci number 0 is even. Is it true or false? It's true. F of 0 is 0. Okay. The second one is saying if Fibonacci number 0 is even, then Fibonacci number 1 is even. True or false? This sentence. Okay? Let me remind you. F of 0 is 0, f of 1 is 1, f of n is equal to f of n minus 1 plus f of n minus 2. But this starts when n is greater than or equal to 2. Okay? So obviously this sentence is false. Okay? For Fibonacci number 1, that is 1. 1 is odd, right? So P of 0, P of Fibonacci number 0 is even, but this is not true. This is true, but this is false. And this case is not covered by this equation. So when you compute Fibonacci number 1, you are not adding the two previous numbers. It's not covered by this definition. So you cannot say that you are adding two even numbers when you find Fibonacci number 1. That's the case where it fails. Okay, are we together here? Okay, so you will see a lot of questions like this in your test. Okay, and most of the time it's actually easy to find once you write down this way and try to reason case by case. All right. All right, so let's summarize the mathematical versus course of values induction. So we saw these two inductions. So so this is a general form. I still have the typo here. So this should be n0 plus 1. So let's see. In the case when you try to prove P of n, where n is any numbers that is greater than or equal to some number n0, some fixed number n0. In mathematical induction, the base step is you prove the first number, P of n0. And in the inductive step, you assume that P of m is true and then try to prove the very next case, P of n plus 1. In other words, when you try to prove P of n plus 1, you can use only one induction hypothesis about m. Okay? Course of values induction doesn't necessarily distinguish with different base case. Base case is actually part of the inductive step. What you show is for every number m greater than or equal to the base number n0, when you prove P of m, you can assume all preceding numbers, for all preceding numbers, this property holds. Okay? You can use any induction hypothesis along this list, okay, to establish that P of m is true. Okay? Now, when we do the proof in Fibonacci number, we had to use the two induction hypotheses. To prove P of m case, we use P of m minus 1 as well as P of m minus 2, which cannot be established by mathematical induction. Because in mathematical induction, when you try to prove P of m, the induction hypothesis that you can use is only about m minus 1, P of m minus 1. Okay? Nonetheless, we are not going to cover this in this class, but there is a transformation to turn the proof in mathematical induction into a course of values induction and vice versa. That transformation is actually very complicated. In principle, it is possible that you can, whatever you can prove in mathematical induction, you can prove in course of values induction and vice versa. But those proofs may not be that simple and natural. Okay? So sometimes, and this is actually a topic for the next class, we are going to prove some properties of propositional formula. Many of the times we are going to rely on course of values induction, okay, rather than mathematical induction. All right, any question after this part? If not, then let's close.